All right, on example 7, the bar graph from the figure is based on data from the Nevada Department of Motor Vehicles. The graph illustrates the distance in feet a car travels between the time in seconds the driver recognizes an emergency and the time the brakes are on. So it says time in seconds, but it's actually based on speed of the car. All right. So if the car is traveling 25 miles per hour, the person's going to move 27 feet before they realize there's an emergency and they'll hit the brake. They'll still have some stopping distance on top of that. So this is just the amount of time it takes from the moment a person notices a problem to the amount of time it takes their foot to hit the brake to start stopping them. And then, of course, depending on speed, it's going to take some time to stop. So there's still some stopping distance in addition to that, but we're just dealing with the reaction time here. How long does it take the normal person driving at these speeds? How far will they travel before they actually hit the brake? They want us to find a linear function that models the reaction distance in terms of speed of the car by using the ordered pairs 25, 27, and 55, 60. Okay? So the horizontal axis here is the v-axis, v for velocity, speed. And the vertical axis here is the d-axis, representing distance in feet. Okay, the first thing before I start working on a problem involving any kind of a chart, bar graph, set of ordered pairs, whatever, is I make sure I get a complete understanding of what the horizontal and vertical axes represent. All right? These bars represent kind of like ordered pairs, 25, 27, 35, looks like about 38 maybe, 45, 49, 55, 60, 65, 70. They're kind of like ordered pairs. How fast I'm going compared to how far I go. All right? The ordered pairs they're concerning us with are 25, 27, and 55, 60. They want me to find a linear function, straight line. Anytime it says find a line, we're looking for slope and y-intercept, right? So we're thinking y equals mx plus b. For the sake of this problem, though, instead of y, what do I use?
D.
D. Instead of x, I use?
V.
V. All right? Because again, those are the variables being used in this problem. All right? So, what I know about slope is that slope is equal to change in y over change in x. So y is 60 and 27. 60 minus 27 on top, change in y. And then on the bottom I'm going to start with 55 because I started with 60 on top. Subtract 25. That's x minus x. Okay, order is important in the sense that the order has to be the same. Okay, doesn't matter what order you put the top as long as you put the bottom in the same order. 60 minus 27 is equal to 33. 55 minus 25 is 30. Usually I like fractions more than decimals. For the sake of this problem though, if I was trying to figure out speed or feet, I think a decimal has to be more meaningful. I was going 75 fourths miles per hour, or I was going whatever that is as a decimal. 18.75 miles per hour. That'd be more meaningful, right? So a decimal answer is probably more meaningful here. So let's go 1.1 there. 33 divided by 30 is about 1.1, or exactly 1.1 actually. Reduces to 11/10. Decimal point goes one space over. So 1.1 is the slope of the line. And again, I've got my structure here, d equals mv plus b. Once I know the slope is 1.1, I can simplify it. Instead of d equals mv plus b, I can change m to 1.1, so now d equals v plus 1.1 v plus b, right? If I want to figure out what v equals, I take one of my two ordered pairs, doesn't matter which one. I'm going to take the blue one because the numbers are smaller. So 27 is the distance when 25 is the velocity. Make sure you put them in the right spot. The y-coordinate 27, x-coordinate 25, multiplied by the slope. That gives me 27 equals 27.5 plus b. Move the 27.5 over, subtract. And that gets me b is equal to negative 0.5. So my linear function representing this problem is the reaction distance in feet is equal to 1.1 times the velocity minus 0.5. There's my linear function. This chapter is titled Linear Functions. So you should expect almost everything in this chapter to be about lines and linear functions. So this type of structure almost always is going to be happening in this chapter. all right, especially in the word problem section. Expect linear functions. Chapter 2.4 is called Quadratic Functions. Same types of problems, now they're going to be curvy like a parabola instead of straight like a line. All right. Now for part B it says, what reaction distance does the model predict for a car traveling 50? Notice there's no 50 miles an hour here, right? Mm-hmm. So what we've created here is called a trend line. And you can see the bars, if you look just at the top of the bars, they look like they line up in a straight line, pretty much. So here's 25, 27, here's 55, 60. If I connect those dots with a nice straight line, like so. Okay, they only got 5 data points to get any kind of information, but that's called a trend line. It shows us the trend. As the speed increases, the distance increases. That's the trend. Does that seem reasonable? If you're going faster, you're going to go further before your foot hits the brake. All right. So there's no data here for 50, but notice the line crosses through 50. So that's what that green line is, what this equation here represents. So if I know how fast I'm going, I know the velocity, I can find the distance. So the distance traveled going at 50 miles an hour, if I replace v with 50, so 1.1 v minus 0.5, so 1.1 times 50, our traveling speed, minus 0.5. That gets me d equals 55 minus 0.5. So the distance traveled should be about 54.5 feet. And I know that's feet because it says reaction distance in feet. So you should be able to use the chart also to establish the correct units on your answer. Before you do the practice problem, I want to bring to your attention some stuff happening in the practice problem real quick. So I'm going to bring this to a new page. The practice problem involves the years 1997 through 2003. And the credit card debt for America in billions of dollars. If I get something wrong here, correct me. The first year is 1997, the debt was $531 billion, right?
Yep.
Yeah.
And then 1998 is what?
562.5.
1999?
598.0.
Yeah.
Yeah.
All right, and then 2000?
667.4.
And 2001?
701.3.
2002?
712.0.
712. And finally 2003.
725.0.
Alright, so that's our data. Okay, now let's just make sure we can make complete and total understanding of this. $531 is now what all the Americans in the world owe in 1997. $531 billion is what they owe. $562.5 billion, $598 billion, $677.4 billion. So if they ask, when will the amount be, was it $850 billion, I believe is what it's asking for?
Mm-hmm.
Yeah.
All right, $850 billion. The y-coordinate is going to be 850. All right, the x-coordinate represents the year. Okay, let me show you one other thing the book does quite often in these year problems. They assign a value to the first year as 0. The beginning year in this problem we'll say is t equals 0. So this would be t equals what?
1.
Very good, 1. And 2 and 3 and 4 and 5 and 6. Right? Now what does part A do? What do they ask us to do?
Using the data for 1997 and 2003.
Stop. Okay, using the data for 1997 and 2003, construct.
Find a linear model that predicts the amount of revolving consumer credit in billions for year t around the slope to the nearest 10th.
Year t. So I'm going to use t equals 0. Here's why. Okay? 0 is a small number, 1997 is a big number. There's why. The end. That's why. Okay? If I use t equals 0, it's easier than if I use t equals 1997. All right? Now, if I do this, though, and I end up with t equals 8, that's 2005. I have to add 8 to the beginning year. If I get t equals 4, that'll be 2001, because 4 years beyond 1997. So if I want to do this to make the number smaller, make it easier, I also have to interpret my answer a little bit. But again, the book does this quite often, so get accustomed to it because it happens almost all the time. So then when I use this data here, my ordered pairs are 0, 531 and 6, 725. Then it's exactly the same as this car problem we did a moment ago. We've got 2 points of reference. We want to find the equation, linear equation, they said to predict a linear model, right? So the slope is going to be 725 minus 531 over 6 minus 0. That's 194 over 6, which comes out to 32.3 repeating. Okay, and for the sake of making the problem simple enough, let's just go 32.33. That'll be close enough. A couple decimal places will be fine. All right. If I go to y equals mx plus b, if I use this point here, here's another advantage using t equals 0. 0, 531 is the y-intercept. Right? If x is 0, y is 531, that's the y-intercept. If x is 1997 and y is 531, that's not the y-intercept, that's some number way out there. I still have to find a y-intercept. Okay? So that's another advantage using t equals 0 for the first number. That immediately makes the y-intercept. So b is equal to 531. And just like that, I can make this equation. The det, I'm going to use capital D for det, equals the slope, 32.33, times the year, I'm going to use t, plus 531. So if I know what number year it is, I can stick it in there to figure out what the det would be. If I know what the det would be, I can figure out what number year it is. Okay? Now, the part B of this problem, that's part A done. That's assuming t equals 0 is 1997. If you do that, make sure you make note of that on your function, that what t represents, because it does not represent these numbers, it represents these numbers I assigned to them. Okay, so if you're going to make this t equals 0 be a year, which again, the book quite often does, and I would expect you to do it too, because it's easier. All right? Makes the numbers much smaller and easier to manage. Part 2 asks you to find what year does the debt reach $850 billion. Debt is D. So $850 billion, so D is just 850. If I solve that, I'm going to get t equals some number. Yeah, I'll let you guys solve that. You guys know how to solve. But you can go through the work necessary to get it. I'm getting 9.86 when I do it. 9.87. Okay. Now, that's not the answer to the question. Okay, going back to the question, if you look carefully at what the question says, in what year will the debt reach $850 billion?
You have to add that to 2003.
No.
No.
Have to add that to 1997.
Oh, okay.
Whatever your 0 year is, you're going to add your t value to that year to get the correct answer. So 1997 plus 9.87 years comes out to 2006.87, right? All right. 2006 is what year it is. 0.87 puts us somewhere in October, maybe. October, November, somewhere in there probably. All right. It asks what year it happens. The year it happens is 2006. If it's 2006.99, that's December 30th. It's still 2006. So if it's an in what year problem, you're letting t represent the year 0. T equals 0 represents some year. Add your answer to the 0 year to figure out what year it is. And truncate. That means chop the decimal. Don't round. Chop it off. 2006.01 all the way up to 2006.99 all represent the year 2006, just a different day in 2006. So if it says in what year did it occur, that's how you handle it. So the answer to part B would be 2006, would be the year it occurs. You can use the 1997 through 2003, you would have gotten the same answer. It's just this number would have been a much larger negative, and the equation you get would have been a lot more difficult to handle. So it's advisable to do that t equals 0 deal when you're dealing with years.